Good morning, good afternoon, good evening. This is Professor T. Freed Muhammad, the lecture series PhD Artificial Intelligence, 830, University of Cumberland at Kentucky. We'll be looking at actor critique and continuous control. So last lecture, we built reinforce the simplest policy gradient algorithm. It worked, but it had a fundamental structural problem. You had to wait for the complete episode before making any gradient update. And the Monte Carlo returns it used were so noisy and that training was painfully slow. Both of those problems have the same root cause. Reinforce has no value function. It has to observe actual returns to know whether things went well, and that takes time and accumulates variance. Today we fix both problems by introducing a second network, the critic, whose job is to estimate value online so the actor does not have to wait. The second half of the lecture extends everything to continuous action spaces. Most real-world control problems, robotics, autonomous driving, physics simulation have continuous actions, and DQN style methods simply don't work there. We'll see how a Gaussian policy handles it, and then close with the three stabilization techniques that make actor critic training reliable in practice: entropy regularization, normalization, and PPO's clipped objectives. This lecture is dense but directly applicable. PPO is the algorithm running behind most state-of-the-art reinforcement learning deployments today. So 5 sections we'll discuss today, each building on the last. We open with the actor critic framework itself, the two network architecture that each network does, and how they interact through the TD error signal. Second section goes deep into TD error, what it means mathematically, why it replaces the Monte Carlo return, and what its signs of delta tells the actor about its last action. Third section introduces the advantage function, which is the cleanest way to formulate the actor's learning signal, and quantity you will see referenced throughout the modern reinforcement learning literature. Fourth section moves to continuous control, why discrete methods break, how Gaussian policies work, and the reparameterization trick that makes gradient-based training possible. Fifth section covers the practical engineering that makes all of this stable: learning rate choices, normalization, entropy bonuses, and PPO. We close the comparison table that tells you when to reach for a policy gradient method versus the value-based one. By the end, you should be able to implement a working PPO agent from scratch. Actor critique. Reinforce gave us the core idea. Take the gradient of log probability of your actions weighted by how good the outcome was. The weakness was in how we estimated how good we weighted for the entire episode, summed up the discounted rewards, and used that as the weight. That estimate is unbiased but enormously noisy, because the total return mixes the quality of one specific action with the randomness of every subsequent transition in the episode. The actor critic framework breaks this into two separate responsibilities. The actor is the policy network, it decides what action to take. The critic is a value network. It estimates how good the current state is rather than waiting for the episode to end. The critic provides a real time estimate of value after every single step, and that estimate gets used immediately to update the actor. This makes the algorithm fully online. It learns from every transition and dramatically lowers the variance of the gradient signal because the critic's value estimate is much smoother than a raw Monte Carlo return. Let's trace the information flow in the diagram. At the top is the current state S, which gets fed to both the actor and the critic simultaneously. The actor takes S as an input and outputs a probability distribution over actions. For discrete tasks, a softmax over logits. For continuous tasks, a mean and standard deviation. An action is sampled from the distribution and executed in the environment. The environment returns a reward R and the next state S prime. Those get fed to the critic, which evaluates the next state's value V of S prime and compares to its prediction for the current state V of S. The difference, the TD error delta, flows back to the actor as a teaching signal. Positive delta means the action exceeded the critic's expectations, so the actor increases the probability of the action. Negative delta means disappointment, so the actor decreases it. Crucially, both network update from every single step. There is no waiting for episode end, no accumulation of noise across hundreds of transitions. The actor is neural network with parameter theta that takes the state as input and outputs a distribution over actions. For discrete environment, it outputs a softmax distribution. The probability of taking each possible action. For continuous environments, it outputs the parameters of Gaussian distribution, a mean and standard deviation for each action dimension. At every step you sample from this distribution, execute the sampled action and observe what happens. The actor's update rule is theta gets updated by alpha pi times the gradient of log pi theta of a given S times delta. This is exactly the reinforced update, but with delta replacing gt. The replacement is the key change. Delta is computed from a single step and the critic's value estimate. So no episode needs to complete. The sign of delta drives the direction. Positive delta increases the probability of the taken action. Negative delta decreases it. The actor also operates under an on policy constraint. It must use data from its current policy. PPO relaxes this with an importance weighted objective, which we cover in upcoming slides. The critic is a separate neural network with parameters phi that takes the same state as input and outputs a single scalar. The estimated value V phi of S. This is the critic's best guess at how much cumulative discounted rewards an agent can expect from this state onward under the current policy. The critic is purely an internal component. It never directly influences what action is taken, only what the actor learns from the action after the fact. The critic is trained by minimizing the squared TD error. Phi gets updated by gradient descent on the expectation of delta squared. This is just regression. The critic is learning to predict the bootstrapped return R plus gamma V phi of S prime. The quality of the critic directly controls the quality of the actor's gradient estimates. A poor critic produces biased delta values that mislead the actor. A good critic produces single signal in reality that closely tracks the true advantage of the taken action. In practice, the critic is often given a higher learning rate than the actor. It needs to converge faster so the actor has a reliable teacher to learn from. The TD error delta T is RT plus gamma times V phi of S T plus 1 minus V phi of ST. Let's unpack this term by term. RT is the reward actually observed after taking action AT, the only direct feedback from environment. Gamma times V phi of ST plus 1 is the critic's bootstrapped estimate of future value from the next state. This is what replaces the need to observe the rest of the episode. V phi of ST is what the critic predicted at the start of the step. Delta is the difference between these two, how much better or worse things turned out than critic expected. The full actor update is theta gets updated by alpha pi times the gradient of log pi theta of AT given ST times delta T. Compares this to reinforce. The structure is identical, but GT has been replaced by delta T. The replacement has enormous practical consequences. GT required a complete episode, potentially thousands of steps, and accumulated variance required complete episode, potentially thousands of steps, and accumulated variance from every random event in the episode. Delta T is computed from a single transition, one reward, one value estimate of the next state, one value estimate of the current state. It's available immediately after every step. It incorporates far less noise and it provides a signal even in environments where individual episodes return are highly variable. Why does advantage function matter? Because q pi of s comma a contains two components: how good the state s is to be in and how good the specific action a was relative to the alternatives. V pi of s captures the first component, the inherent value of the state, and subtracting it leaves only the second. This centering removes the noise that comes from being in a particularly good or bad state and focuses the gradient signal purely on whether the action itself was above or below average. In practice, we estimate the advantage of the TD error delta. It is an approximate but computationally cheap estimate of A that requires no separate Q function. Let's put the comparison side by side clearly. Reinforce must complete a full episode before any update, cannot handle continuing tasks, and generate highly variable gradient estimates because GT accumulates randomness across the entire episode. On top of that, it is severely sample inefficient. One gradient update per episode means you might collect thousands of environment steps to make a signal, in reality, make a single parameter change in sparse reward environments. It barely learns at all. If GT is near zero because reward is rare, the gradient signal is near zero too. Actor critique addresses every one of these problems. Updates happen after every single step, no waiting for episode end, which means it works on continuing tasks, provide far more gradient updates per unit of environment interaction, and generates how much lower variance update because delta involves only one step look ahead rather than a full trajectory sum. The critic also provides a meaningful signal even when environmental reward is sparse. The value function can distinguish a good state from a bad one even if no reward has been received yet. The price is biased from the critic's approximation error, and but in practice this trade-off is almost always worth it. Continuous actions. For the first half of this course, we have been dealing with the discrete action spaces, a finite set of choices the agent can take. Atari games, grid worlds, board games, these all have discrete actions, and DQN handles them well. But the majority of real engineering problems have continuous actions. A robot arm does not choose from a menu of positions. It applies continuous torques to each joint. A car does not choose from a list of steering angles. It applies a continuous steering input. An aircraft does not pick from a set of throttle settings. It modulates continuous thrust. So let me be precise about why DQN fails on continuous actions. DQN's policy is take the action with the highest Q value. In a discrete space with four actions, this is a table lookup in a continuous space with an infinite number of possible torque values. This requires solving argmax over a maximized Q of SA, a non-convex optimization problem that in general has no efficient closed form solution. You would have to run gradient ascent on the Q network every single step just to select an action, which is computationally prohibitive. The standard solution is Gaussian policy. The actor network outputs a mean mu or mu and standard deviation sigma for each action dimension, and the action is sampled from the resulting Gaussian distribution. Written mathematically, A is drawn from n of mu theta of s, sigma theta of s squared. The subscript beta makes explicit that both the mean and variance are functions of that state computed by the neural network. For a continuous control task with k action dimensions, the actor network outputs two k scalars, k means and k standard deviations, one pair per action dimension. The means are typically passed through a tan-H activation and then scaled to the action range. This ensures the mean action is always within the valid action bounds regardless of network outputs. At evaluation time, when you want deterministic behavior, you simply use the mean action directly without the sampling. Here's a subtle but critical issue. The actor network outputs mu and sigma, and then we sample an action from n of mu sigma squared. That sampling step is stochastic operation. It is not a differentiable function of mu and sigma. Gradients cannot flow backward through a random sample, so if we want to compute gradients of the objective with respect to theta using the sampled action, we have a problem. The computation graph is broken at the sampling step. Training actor critic methods on continuous control is genuinely difficult. The central challenge is that the actor and the critic are coupled, they influence each other, and both are being updated simultaneously. On non stationary data, a bad critic update produces biased delta values, which cause bad actor updates, which changes the policy, which changes the data distribution the critic is trained on, which makes the critic wrong again. This feedback loop can spiral into instability rapidly. Two specific failures modes are common. First, gradient explosions. Large policy updates move the distribution far from where the critic's value estimates are valid, causing the next batch of delta values to be wildly inaccurate, producing an even larger update, and so on. A runaway spiral that crashes training. Second, hyperparameter sensitivity. Unlike supervised learning, where you can tune against validation loss, in reinforcement learning, there is no clean external metric to optimize. A learning rate that works perfectly on one environment can cause divergence on a slightly different one. Actor and critics often need separate learning rates, and ratio between them matters. The non-stationary of the target R plus gamma V of S prime, which changes every time phi updates, is an additional source of instability that target networks used in SAC and TD3 are designed to address. Good algorithm design gets you to the door of a working continuous control agent. Good optimization engineering gets you through it. Even with a correct actor critic implementation, training can fail silently. The agent makes some progress and then plateaus or trains well on the seed but collapses on another, or diverges from 100,000 step when it seemed to be going well. These failures are almost always due to numerical issues that three categories of a technique address: learning rate and gradient management, input and reward normalization, and entropy regularization. This section is intentionally practical. The three techniques we cover here are not exotic research contributions. They are engineering defaults that virtually every serious continuous control implementation uses. If you start with a PPO or A to C code bases and it is not working, the first things to check are all on this slide. Your observations normalized, are your rewards normalized, is your gradient norm being clipped, and is your entropy efficient non-zero? Fixing any one of those can return a failing run into a stable one. Learning rates, let me repeat myself. The stabilizing techniques are based on learning rate scheduling and gradient clipping are the first line of defense against instability. Using a separate higher learning rate for the critic than the actor makes sense. The critic needs to converge quickly so it can provide a reliable signal to the actor, while the actor should update continuously and cautiously to avoid moving the policy so far that critic estimates become invalid. Gradient clipping by global norm, capping the total gradient magnitude at a value like 0.5, prevents any single bad batch from causing an explosion. Atom optimizer with epsilon set to 1E5 rather than the default 1E8 is more numerically stable for reinforcement learning objectives where gradient scales vary wildly. Standard policy gradient updates have a dangerous failure mode. If the gradient step is too large, the new policy can be wildly different from the old one. The data you collected was generated by the old policy, and if the new policy is very different, those importance weights are invalid. The gradient estimate is wrong. In practice, this means training collapses, the policy overshoots to a degenerate distribution, performance crashes, and often does not recover because the bad policy is now generating bad data. And for the next update, PPO addresses proximal policy optimization. PPO. I thought to keep it always PPO so you can conduct a research and figure out what is proximal policy optimization. The PPO addresses this with the importance ratio and a clip operation. The importance ratio RT of theta is the probability of the taken action under the new policy divided by its probability under the old policy. If this ratio is close to 1, the policies are similar and the update is valid. The clipped surrogate objective takes the minimum of two quantities, the unclipped advantage weighted ratio and the version before where the ratio is clipped, to the range 1 minus epsilon to 1 plus epsilon. This clip acts as trust region. It prevents the objective form incentivizing updates that move the policy too far from the data in generating distribution. PPO adds a value function loss term and an entropy bonus to this clipped objective. So once again, proximal policy optimization is the key learning that you all should pay decent attention to learn all these algorithms appropriately. The choice between policy gradient methods and value-based methods is primarily driven by the structure of the action space. For continuous and high-dimensional action spaces, robot control, fluid dynamics, physics simulation, policy gradients methods are the only viable option. They parameterize the policy directly as a Gaussian or other differentiable distribution, handle continuous outputs naturally, and don't require an argmax over action space. PPO is a default starting point for most continuous control tasks. SSC is preferred when sample efficiency is critical because it uses a replay buffer and can learn from off policy data. So I'm not going to go through this because I have been discussing the ActorCritic combines best of both. Advantages centers the signal. Stability requires engineering. TD error replaces Monte Carlo return. Gaussian policy for continuous control. And PPO is the practical default. So I strongly suggest you to conduct research in the arena of PPO to understand this more in depth, and wish you best happy learning. See you in the next lecture.